Out in the depths of space, the James Webb Space Telescope is already revolutionizing what we thought about the universe. For James Webb, the hits just keep coming, one riveting image after another, from the far reaches of the universe to planets right here in our own solar system. We got our first taste a year ago, and the images did not disappoint. The Carina Nebula, Stephan's Quintet, and, spectacularly, this so-called deep field image showing thousands of galaxies stretching into the distant universe. But perhaps the most amazing thing revealed by James Webb is that the furthest you look back in time, there were already huge, mature, and fully formed galaxies that shouldn't exist. Some of them even might be older than the universe, and scientists call them universe breakers. Nobody expected them. They were not supposed to be there. And now, nobody can explain how they had formed. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb's shocking discoveries could shatter our leading explanation for how the universe began. Originally, the Big Bang was a simple idea that grew out of three facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these three facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. We can extrapolate this back farther and farther, to even very early times if we like, and recognize that our modern universe must have emerged from a denser, smaller, more uniform state in the very distant past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation with a blackbody spectrum in all directions, arising from when the universe cooled through the threshold that enabled it to form neutral atoms. That the universe would have, at even earlier times, been hot and dense enough to initiate nuclear fusion reactions before any stars could form, leaving us with an initial abundance of elements other than hydrogen among the pristine set of atoms that the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually, the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are three additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang. How hot and dense it was, what the initial spectrum of density imperfections were, including that were all adiabatic Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the Standard Model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time-evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when, in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continue fuel doubts about the Big Bang Theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy GNZ11 at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 1 year after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 400 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 already is now only the 5th most distant galaxy known, and it's fully expected that over the next months, not only will the current cosmic record for distance, jot as GSZ13-0, from a time just 320 million years after the Big Bang, be broken, but that at least dozens of new ultra-early, ultra-distant galaxies will soon be confirmed. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. It is clear that galaxies captured by James Webb are so massive that they should not be possible under current cosmological theory. Thus, Big Bang astronomers are now stunned and surprised because, according to the Big Bang theory, those galaxies shouldn't be there. There should have been only primordial dust from which they assume that stars and galaxies originated after a primeval explosion. The James Webb Telescope is challenging the Big Bang theory held by most scientists, and it is causing consternation in the scientific community, at least among those scientists who believe in the Big Bang origin of the universe. Big Bang scientists believe that the expansion of galaxies in the universe came from a singularity that exploded billions of years ago. Yes, some galaxies may be expanding, moving further away, what is called red shift. But this is not necessarily the case with the entire universe, and not even all scientists, including evolutionary scientists, interpret red shift in our universe as meaning galaxies are expanding, or that there was a primeval Big Bang from which the universe sprung, it has been said that publishers of prestigious science journals refuse to publish papers and research from scientists who refute the Big Bang theory. Canadian physicist and scientist David Rowland asserts in his internet article, "The Big Bang never happened," several scientific contradictions to the Big Bang that have been conveniently glossed over or ignored in order to support the much-cherished Big Bang theory held by the majority of scientists. These scientists have had to resort to the internet to publish their scientific arguments refuting the Big Bang theory. Rowland says that the red shift in actuality is not a measurement of velocity, of showing that galaxies are expanding and moving away, but only a measurement of temperature and distance. He says that Big Bang scientists initially confused the red shift from galaxies with the Doppler effect, and this confusion led these earlier scientists to believe that the universe was expanding. Rowland points out that the light from galaxies naturally attenuates over long distances, and that this attenuation had been wrongly interpreted by early scientists as evidence that galaxies in our universe must be expanding. Once this belief had set in early on, it continued to be taught and held by the majority of scientists to this day. Even the famed astronomer Edwin Hubble, after whom NASA named its famed telescope, and who discovered the redshift, expressed doubts about interpreting the redshift as evidence that galaxies are expanding. Hubble believed there could be other reasons for the redshift. Hubble refused to believe that the redshift was proof of galaxies expanding. Even if there was a past expansion of galaxies, this does not mean that the galaxies at present are expanding. We can only see the past from telescopes, not the present. Interestingly, the Bible teaches that the heavens at one time expanded. Various passages in the Bible speak of God stretching out the heavens. If the Big Bang really occurred, there would have been a uniform distribution of gases in space. This uniform distribution of gases throughout the universe would have made sure that the gases didn't have enough gravitational attraction to form into planets and stars. Big Bang scientists must assume the existence of dark matter in the universe to provide enough gravitational force for stars and galaxies to form. However, there still is no scientific proof for the existence of dark matter. In fact, the hypothesis of the existence of dark matter has been increasingly discredited by science. Big Bang scientists believe that dark matter can be the only gravitational explanation for how galaxies behave. However, other scientists have successfully shown an alternative explanation to dark matter known as MOND, which stands for Modified Newtonian Dynamics. In other words, it is not necessary to believe that 80% of the universe must be made up of dark matter in order to explain certain behavior and movement of galaxies. The late creationist and scientist Dr. Duane T. Gish said, "The galactic structures discovered during the past few years, however, are so massive that even if cold dark matter did exist, it could not account for their formation." Furthermore, an explosion cannot explain the precise and orderly orbits and courses of thousands of billions of stars in thousands of billions of galaxies. Gravity may explain how that order is maintained, but mere gravity cannot explain the origin of that order. The disorder in the universe can be explained because of chance and random processes, but the order can only be rationally explained because of an intelligent power. Some evolutionary astronomers believe that trillions of stars crashed into each other, leaving surviving stars to find precise, orderly orbits in space. Not only is this irrational, but if there was such a mass collision of stars, then there would be a supermass residue of gas clouds in space to support this hypothesis. The present level of residue of gas clouds and dust in space doesn't support the magnitude of star deaths required for such a hypothesis. It's more rational to believe that stars die and decay into gas clouds and dust instead of believing that gas clouds and dust evolve into stars, as evolutionary astronomers teach. Evolutionary astronomers only assume that gas clouds and dust in the so-called pillars of creation are birthplaces for stars. This assumption is conveniently passed on as fact in textbooks and media. In another remarkable effort to explain Webb observations, the scientist proposed a hybrid model that combines aspects of the tired light model and a cosmological model based on evolving coupling constants. This new model suggests a longer galaxy formation time, allowing for the formation of well-evolved early galaxies. However, further research and scrutiny are required to determine if this model can provide a satisfactory explanation for all the observations in cosmology. On the other hand, the need for a new cosmology is not unprecedented in the scientific community. Mixing models to explain new observations has been done in the past, such as Albert Einstein's explanation of the particle-like and wave-like nature of light. Similarly, estimating the age of the universe based on the age of stars in globular clusters has also been used as an alternative method. In conclusion, the discrepancies between observations and the standard model of cosmology have prompted the proposal of a new model that suggests a longer age for the universe. While this new model shows promise, further research is needed to determine its validity and if it can provide a comprehensive explanation for all cosmological observations. And as a worth note, the eagle eye of James Webb has just discovered two of the most distant galaxies ever seen, supporting the basic picture of galaxy formation as described by the Big Bang theory. The discovery was made possible thanks to a huge helping hand from a massive gravitational lens in the form of the galaxy cluster known as Abell 2744, nicknamed Pandora's cluster, which is located about 3.5 billion light-years away from us. The immense gravity of the cluster warps the very fabric of space-time sufficiently to magnify the light of more far-away galaxies. Using the James Webb Space Telescope to search for early galaxies magnified by this cosmic lens, Bingji Wang of the Penn State Eberly College of Science and member of the James Webb Space Telescope Ultra-Deep Near-Infrared Spectrometer and Near-Infrared Camera observations before the Epoch of Rionization or Uncover team discovered two of the highest redshift galaxies ever seen. Cosmological redshift, as told, is the stretching of light wavelengths provoked by the continuous expansion of the universe. The more distant a galaxy is, the more the universe had expanded while that galaxy's light traveled across space to reach us, and therefore, the more the wavelengths of that light are stretched. As wavelengths get stretched out in this manner, they go from tighter, bluish ones to redder ones, eventually falling into the invisible infrared region of the electromagnetic spectrum. Galaxies that existed just between 300 and 400 million years after the Big Bang have had their light stretched into those infrared wavelengths that can't be seen by humans, but can indeed be detected by the Webb's near-infrared camera and near-infrared spectrometer instruments. Wang and her team were able to identify the lensed images of two high redshift galaxies. One, designated Uncover Z13, Z is shorthand for redshift, has a redshift of 13.079, confirming it to be the second most distant galaxy known. The most distant confirmed galaxy is Jade's GSZ 13.0, which was also discovered by the James Webb in 2022 and has a redshift of 13.2. We see Uncover Z13 as it existed just 330 million years after the Big Bang. The other galaxy recently discovered, Uncover Z12, has a redshift of 12,393, placing it in fourth place in the all-time list of most distant galaxies. We see this realm as it was just 350 million years after the Big Bang. What marks the two Uncover galaxies out as different is their appearance. Other galaxies seen at similarly high redshifts seem to be point-like, indicating they are very small, just a few hundreds of light-years across. The Uncover galaxies, on the other hand, have structure. Previously discovered galaxies at these distances appear as a dot in our images, Wang said in a statement, but one of ours appears elongated, almost like a peanut, and the other looks like a fluffy ball. These galaxies are also bigger, with Uncover Z12 sporting an edge-on disk about 2,000 light-years across, which is 6 times larger than other galaxies seen in this era. It is unclear if the difference in size is due to how the stars formed or what happened to them after they formed, but the diversity in the galaxy properties is really interesting, said Wang. These early galaxies are expected to have formed out of similar materials, but already they are showing signs of being very different than one another. Although the dichotomy in galaxy properties, even at this early stage in the universe, is eye-opening, both of the newfound realms have general characteristics that are strongly supportive of the Big Bang model. This model describes how, in the aftermath of our universe's creation, galaxies began life small before growing rapidly through mergers with other galaxies and gas clouds. This growth, in turn, spurred more star formation, which ultimately increased the abundance and variety of elements contained within the young galaxies, introducing substances to them that are heavier than hydrogen and helium. The galaxies uncovered by Uncover, if you'll pardon the pun, are young, small, have a low abundance of heavy elements, and are actively forming stars, all of which supports the whole paradigm of the Big Bang theory, Joel Leja, who is an assistant professor of astronomy and astrophysics at Penn State University and a co-researcher on Wang's team, said in the statement. Interestingly, the Webb telescope has the ability to see even higher redshift galaxies than Uncover Z13 and S12, meaning they'd be even younger, but it didn't detect any being lensed by the Pandora cluster. As Leia said, that could mean that galaxies just didn't form before that time and that we're not going to find anything farther away. Or it could mean we didn't get lucky enough with our small window. Astronomers will keep looking, using a multitude of lensing clusters to open up new windows into the deep universe in search of some of the first galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.